8.5 Spontaneous decay. It is also known as nuclear decay or radioactivity, where the nucleus of an unstable atom will lose energy by emitting radiation or particle. If you can see on your periodic table, there are some elements that are radioactive. Okay, so they have their own half-life and they undergo decay process according to their half-life. From the decay process, it will emit radiation in formation of new elements or decrease the energy of the nucleus. A material or element that spontaneously emits such radiation is considered radioactive. So it's very dangerous because it can emit radiation spontaneously. When radioactive nuclei undergo decay process, the nucleon number and proton number are conserved. So the total nucleon number on the left side should be equal to the total nucleon number on the right side of the equation. Same goes to the proton number. There are three types of radioactive or spontaneous decay process. First, alpha decay. Second, beta decay. And third, gamma decay. If the radioactive atom undergoes alpha decay, it will spontaneously emit alpha particle. If it undergoes beta decay, it will spontaneously emit beta particle, while for gamma decay, the atom will spontaneously emit gamma ray. This is the example of uranium. Uranium is one of the most unstable elements. It will undergo spontaneous decay according to its half-life, and it either can emit alpha particle, gamma ray or beta particle, and also neutrons and proton. In order for spontaneous decay to occur, the mass of the parent nucleus must be greater than the daughter nucleus and the radioactive particle produced. For example, let's say we have element X undergoes decay. It will produce element Y plus Z plus alpha particles and also energy. So the parent nucleus is on this left side or before the process, and the daughter nucleus is the new element. Radioactive particle is this, for example, this alpha particles, and this is the energy released during the process. So the mass of the parent nucleus must be greater than the daughter nucleus plus with the radioactive particle produced. Why does the mass are not same for before and after the process? This is due to the mass defect that will be converted into energy or photons. How to find the mass defect? Use this equation. Delta M equal to summation of mass before or on the left side, or you can also say that the summation mass of the parent nucleus minus with the summation mass on the right side of the equation, or after the process, or on the daughter nucleus plus with the radioactive particles. Okay, so it depends on the equation. Then you can find the delta M to substitute into the equation. E equal to delta M C square. Here you can have the energy released during the spontaneous decay. Now let's look at the alpha decay. It is the emission of helium-4 to nucleus. During the spontaneous decay that will emit alpha particle, the changes that occur are the proton number will decreases by 2 while the nucleon number will decreases by 4. Let's say we have element X and then it undergoes spontaneous decay to form a new element X, alpha particle or helium, plus with energy released during the process. Another example, let's use uranium. It will undergo alpha decay and produce a new element, alpha particle or helium, and also energy released during the process. We can call uranium as the parent nucleus, while the thorium as the daughter nucleus, helium as the alpha particle, and Q is the energy released. Example 8.11, write an equation for each of the radioactive decay that produce alpha radiation or alpha particle. A. If the polonium undergoes alpha decay, it will produce a new element. You can use symbol X to represent the element, plus with alpha particle and also energy. B. We have radium. It will produce a new element. If you don't know what is the new element, either you can refer to the periodic table or you can just put X to represent the element, plus with the alpha particle and also energy. Second, for beta decay process, it is the emission of a beta particle, or we call it as electron. The changes that occur are proton number will increase by 1 while nuclear number is unchanged. This is the example. Let's say we have element X that undergoes beta decay. It will produce a new element plus with beta particles. The nuclear number is 0 while the proton number is -1, plus with energy. Another example is this element, radium. It will undergo beta decay to produce a new element, thorium, plus with beta particle and also energy. Example 8.12, write an equation for each of the radioactive decay that produce beta radiation. A. Palladium. It will undergo beta decay, produce a new element, plus with beta particles, plus with energy. For B, we have phosphorus. It will undergo beta decay to produce a new element, plus with beta particle and energy. For C, carbon undergoes beta decay to produce a new element, plus with beta particle, plus with energy. For this new element, if you are not sure what is the element, you can put any alphabet as unknown to represent the element, or you can also refer to the periodic table. Example 8.13, uranium decays through a series of transformations to a final stable nuclide. The particles emitted in the first successive transformation are alpha, beta, beta, alpha, and alpha. Write an equation to represent each sequence of the nuclear transformations. You may use A, B, C, D, and E to represent the daughter nuclides for the successive transformations. Okay, what happened is uranium is very radioactive, so it can undergo few series of decay until it becomes a stable nuclide. So at first, it will undergo alpha decay. After that, it will undergo beta decay again, alpha decay, and alpha decay again. First, let's write down the equation of alpha and beta decay. So it's easier for us to refer to the equation. To solve for this example, we are going to refer to the series of transformation. First, uranium will undergo alpha decay. The equation will be uranium undergoes alpha decay to produce new element A plus alpha particles plus energy. Next, element A will undergo beta decay to produce new element B plus beta particles plus energy. After that, it continues with element B will undergo beta decay to produce element C plus beta particles plus with the energy. And the process continues with element C will undergo alpha decay to produce element D plus alpha particles plus the energy. And the last one will be element D will undergo alpha decay and it will produce the element E plus alpha particles plus energy. So the use of A, B, C, D, and E is just to represent the new element or the daughter nuclides for each decay process. How do we balance the equation? We are going to look at the particles that were emitted during this process. If the particle emitted is alpha, it's also equal to helium-42. If beta, it is the nuclear number is 0, the proton number is -1. So you can balancekan the equation. The third process is gamma decay. The symbol is like this. The emission of energy in terms of photons, gamma rays. So dia adalah dalam bentuk gelombang wave. And the nucleus change from higher level energy state to a lower level energy state. Gamma ray is an electromagnetic radiation of a very short wavelength and high penetrating power. This is the equation. If the element undergoes gamma decay, this is the parent nuclides and this is the daughter nuclides and plus with gamma ray. There is no changes to the nuclear number and proton number. For example, we have barium that undergoes gamma decay. It will still be barium, but during the process, it will emit a photon known as gamma ray. Example 8.14, we have a polonium nucleus undergoes alpha decay to lead nucleus. Calculate the mass defect from the spontaneous decay process. So what happened? Polonium will undergo decay process. It will produce lead nucleus plus with helium or alpha particle plus with the energy. So to find the mass defect, we can use this equation. On the left side or before, we have polonium. And on the right side or after, we have mass of lead plus with the mass of helium or the alpha particle. So let's say the mass is given in the equation. For mass of polonium, it is 209.982 U. Mass of lead is 205.969 U. And mass for helium or alpha particle is 4.004 U. So we will get 9 times 10 to the power of -3 U. This is the mass defect. You can also convert it into kilogram, which is 1.49 times 10 to the power of -29 kilogram. Example 8.15, it is found that the polonium nucleus undergoes alpha decay to lead nucleus. Calculate the amount of energy liberated in this decay or energy released during the process. Second one, the wavelength of the gamma ray produced if all the energy liberated is converted into energy of the photons. For question B, please do correction to these terms. We are going to find the wavelength of the wave produced if all the energy liberated is converted into energy of the photons. Okay, let's do question A. First, we need to write the equation of this alpha decay process. It is polonium undergoes alpha decay to produce lead plus alpha particles or helium plus with energy. So here we can see what are the elements before the process and also elements that after the process. We are going to use equation E equal to delta mc square to get the energy, but find the mass defect. First, by using this equation, mass before is referring to the mass of polonium. Mass after is the total mass of lead plus with helium. Here you will get delta M or mass defect equal to 0.009 U. Convert into kilogram, which is 1.49 times 10 to the power of -29 kilogram. Substitute into the equation of E, then you will get 1.34 times 10 to the power of -12 joule. To find the wavelength of the wave, we can use this equation. E equal to HF, while F is equal to C over lambda. You can combine these two equations. And then from the values that we get from question A, we can find the wavelength, which is 1.47 times 10 to the power of -13 meter. Example 8.16, we have a nucleus of thorium undergoes spontaneous beta decay. So it will produce beta particles. A, write the equation for the decay process by giving names to the new element produced. And B, calculate the energy release if the mass of thorium nucleus and the nucleus of the new elements R, okay, this is the mass of the thorium nucleus, and this one is the mass of the new element. Given that the mass of beta particle is given here. So first let's write the equation. Thorium will undergo beta decay and produce a new element. So we put X to represent the new element, plus with beta particle, plus with the energy. So the new element will have nuclear number of 2, 3, 4, while the proton number is 91, and beta particle, the nuclear number is 0, while the proton number is -1. So the number of nucleon and proton on both sides are equal. Or we can say that the equation is balanced. And then the question asks us to give names to the new element. We can refer to the periodic table and look at the element that has the number of proton of 91 and nuclear number 234. It is also equal to the element protactinium. For question B, to find the energy release, first we need to find the mass defect. According to the equation, the mass defect is mass of thorium nucleus minus with the total mass of the new element plus with beta particle, and we will get 2.55 times 10 to the power of -4 U. Convert it into kilogram. And then substitute into the equation of E equal to delta mc square. So the answer is 3.81 times 10 to the power of -14 joule.